Hello, thanks for joining. We're going to give everybody a few, about 30 seconds, and then we'll get going. Okay, all right, let's get going. Welcome to today's webinar, Reduce Your Risk of Data Loss, Critical Testing Insights for Developers. My name is Rick Kutcipal. I'm a product planner at Broadcom, and I serve on the board of directors of the SCSI Trade Association, and I will act as the moderator for today's webinar. During the webinar, we will be conducting 2 polling questions. So I encourage you to use the on-screen prompts to participate in the polls. Look at the bottom of your screen. There should be a vote button. And with that, then I have Craig Foster and Paul Coddington. Craig is a product line manager for storage and networking solutions at Teledyne LeCroy, and he's a very active member in the SCSI Trade Association. Craig has expertise in SAN, server architecture, storage technologies. He brings a broad breadth of experience in product management and go-to-market strategies. Craig also serves on the board of directors of the FCIA. Paul serves with me on the board of directors of the SCSI Trade Association, where he is our treasurer. He's also co-chair of the SNIA SFF TWIG. Paul works at Amphenol, where he plays a very active role in a variety of standards activities, including T10, T11, and the PCI SIG. He has over 20 years of product design experience, leveraging his deep technical expertise in storage standards. Today, Paul and Craig are going to walk us through some proven methodologies for testing a couple of different aspects of SaaS infrastructures. They've prepared short videos that we're going to watch first, and then we will review the polling questions that we did throughout the webinar, and then we're going to review some questions. So for the Q&A section, please submit your questions with the Ask a Question button. I believe that's also at the bottom of your screen. To start, Craig's going to talk about how to use protocol analyzers with Jammer and exerciser capabilities to test different aspects of the SaaS protocol. With that, Craig.
This video will cover how protocol analyzers with Jammer and exerciser capabilities can be used to test and validate different aspects of the SaaS protocol. The University of New Hampshire's Interoperability Labs defines tests for many different protocols and technologies. They define some SaaS-related verification tests. While the tests were defined for SaaS 2.0 speeds, we have updated our exerciser tests to cover 24 gig as well. By automating these tests, companies can quickly run verification tests on their devices and identify and resolve issues early in the development cycle. Using the Jammer option on a protocol analyzer, validation teams can inject CRC coding or symbol errors, either randomly or programmatically. This allows us to simulate real-world fault conditions and observe how devices respond to corrupted packets, which is critical for validating error recovery mechanisms. In addition to introducing errors, jammers can drop packets and/or primitives. Here we demonstrate how the jammer can drop primitives, not just a frame. This is useful for testing timeout scenarios and retry logic in SaaS devices. The analyzer jammer can monitor both pre- and post-error traffic to analyze system behavior under stress. SaaS primitives are low-level control signals used to manage link-level communication. Examples include align, idle, transmit or receiver ready, synchronization primitives, and break and continue. Packet modification involves altering header fields or inserting D words into payloads. This helps verify how devices handle unexpected or malformed data. The Jammer platform recalculates CRC and FEC encoding to maintain protocol integrity during injection. SAS 4 SPL packets were introduced as part of the physical layer encoding scheme. These packets are not protocol-level constructs like SSP frames. Rather, they are low-level transmission units used to carry data and control primitives across the link. SPL packets are built on 128B, 150B encoding with board error correction, and their role is similar to fiber channels' 66-bit symbols. They define how bits are grouped and transmitted, but they do not interpret or process the SCSI commands. This encoding enables higher data rates and improves signal integrity, especially during link training and high-speed operations. To clarify on the higher data rates, which may seem counterintuitive due to the overhead, without robust encoding, PHYs would struggle to maintain reliable communication at 24 gig due to the noise, jitter, and crosstalk. Encoding makes it feasible to operate at higher rates even though it slightly reduces the bandwidth. SPL packet level control is essential for deep protocol validation. Since SPL packets are fundamental transmission units in SAS4, being able to remove, modify, or insert them allows engineers to simulate low-level faults, timing issues, or malformed traffic that would be difficult to generate otherwise. This is critical for testing how devices handle error correction, link recovery, and adaptive equalization. Jammer level control over SPL packets also enables precise manipulation during link training and speed negotiation, helping validate conformance to the SAS spec and uncover interoperability issues. It's a powerful tool for stress testing PHY behavior, verifying FEC performance, and ensuring robust operation in high-speed SAS environments. It is often important to see the original packet that came in as well as the modified packet. The AJA setup shows traffic before and after an error injection. Depending on the speed targeted, a separate analyzer may be needed for analysis, which will be combined later in the GUI. This dual-channel view is essential for understanding how injected faults alter communication. The jammer supports various configurations, including AJA or all-jammer. It is often important for the jammer actions to occur when the device is already in a specific state. By looking for specific events, the analyzer can take various actions based on the state of the environment. In addition to looking for a single event, a state machine can be created to identify complex states of the traffic and trigger or jam only when certain conditions are met. Advanced test scenarios can include multiple states with branching logic. This enables simulation of intricate protocol behaviors and fault conditions, making it easier to validate device robustness. Use cases include frame corruption, bit flipping, CRC, and primitive removal. These help verify error recovery features like acknowledgements, retry behavior, and timeout handling in SAS devices. Advanced scenarios include speed negotiation, window corruption, PHY handshakes, extensions, and FEC error injection. These tests push devices to their limits and ensure compliance within the SAS 4.0 specification. In SCSI-based transports, it's important to verify how initiators respond to error conditions. One common method is to replace a normal SSP response, such as good, with a check condition status. This allows us to simulate fault scenarios and observe how the initiator reacts. The goal here is not to test specific sense codes yet, but to confirm that the system correctly transitions into error handling mode when a check condition is received. This sets the stage for more advanced fault injection techniques. Building on that concept, this example demonstrates how a jammer can be used to intercept and modify a valid SSP response, transforming it into a check condition with a specific error type, such as an invalid command, and a custom additional sense code and qualifier. For instance, we can simulate an abort task scenario with an ASCQ or overlapped command. This kind of targeted fault injection is essential for validating how initiators interpret and respond to detailed sense data. It helps to ensure that error recovery logic, logging mechanisms, and diagnostics tools behave correctly under the edge conditions. This technique is especially valuable in conformance testing and debugging complex SAS environments. In many protocols, flow control is key to performance and understanding and preventing performance issues. Often jammers are used to exhaust credit and observe both performance impact as well as the robustness and performance of error handling with compromised flow control. By substituting credit-blocked primitives, we can test how targets respond to flow control issues. This includes verifying timeout behavior and reconnection logic. Dynamic channel multiplexing, or DCM, is a link aggregation feature introduced in 24 gig SAS to improve bandwidth utilization and reduce latency, particularly between initiators and expanders or between expanders themselves. It enables up to 4 virtual channels over a single 24 gigs physical link, allowing traffic equivalent to 4 by 6G or 2 by 12G streams to be carried simultaneously. DCM works by tagging each SPL packet with a channel identifier, allowing PHY to dynamically route across multiple logical paths. This breaks the traditional one-to-one initiator-to-target model and supports cut-through routing, reducing blocking and improving overall efficiency. DCM is negotiated automatically during the link setup and is not used between initiators and targets. Instead, it enhances routing and aggregation in the SAS fabric without requiring changes to the existing SAS or SATA devices. By reducing cabling complexity and improving throughput, DCM helps extend the utility of legacy devices while eliminating the fairness issues like drive starvation. By jamming different virtual lanes, we can simulate noisy or hostile environments. Again, the goal is to test different aspects for error handling and link recovery. SAS uses multiple virtual channels, especially in wide port configurations. Jamming one or more channels can help assess crosstalk and signal isolation between them. In addition, SAS uses different fairness algorithms that can be tested with this methodology. It is also useful when stress testing the environment for performance. For more granular control, scripts can be created to simulate a variety of device-related implementations. In this case, we are looking specifically at the link capabilities related to link bring-up. Advanced Connection automates 24 gig link bring-up sequences, including speed negotiation, windows stages, and training. There is also a manual connection option which allows customization of each phase, offering granular control over link negotiation and PHY capabilities. This enables users to test their equipment as if they were connecting to a device that may not be available to the validation team. The SAS protocol begins with an out-of-band handshake, or also known as OOB handshake, a low-speed signaling process used to establish a physical connection between two PHYs before any high-speed data is exchanged. This sequence includes key primitives like COM init, sent by the initiator to signal link initialization, COM wake, sent by the target to confirm readiness. The COM SAS primitive identifies the device as SAS capable, as opposed to SATA. COM reset can be used to clear errors or initialize the link. The primitives are essential for ensuring reliable link detection, device compatibility, and proper transition to the next phase of link setup. Following the OOB, the link enters speed negotiation window, where both devices determine the highest mutually supported data rate. During this phase, transmitter training initialization units, or TTIUs, are exchanged to optimize signal quality and equalization settings. Having an exerciser with complex control over OB handshaking, SNW parameters, and TTIU frames is critical for testing and validation. It allows engineers to simulate edge cases, inject faults, and verify how devices respond to non-standard or stress conditions. This level of control is especially important for conformance testing, which ensures that the devices behave according to the SAS specification as defined by the T10 Technical Working Committee. While T10 defines the standard, it does not enforce compliance through certification programs, so vendors rely on conformance testing to validate interoperability and adherence to the spec. Raw frame provides a fully decoded view of serial SCSI protocol fields. Users can right-click to access detailed protocol information, making it easier to debug and validate frame-level behavior. In this example, we're demonstrating how the combination of an analyzer and its integrated exerciser capabilities can be leveraged for capture and replay testing. By replaying specific link conditions either exactly as captured or with targeted modifications, engineers can simulate a wide range of traffic scenarios. This enables stress testing of devices under controlled conditions, helping to uncover edge case behaviors, validate error recovery mechanisms, and assess protocol robustness. The ability to precisely control replay sequences, including OOB handshakes, SNW parameters, and TTIU frames, is essential for thorough conformance testing and debugging interoperability across different SAS implementations. Target emulation scripts can be built from real traces. By modifying sample scripts and inserting actual data patterns, users can simulate realistic device responses for thorough testing. I hope this video has showed how protocol jamming, exercising, and analysis can uncover hidden issues in SAS devices, whether it's corrupting, dropping, or modifying packets, or simulating complex link bring-up scenarios. With automation, state control, and real trace emulation, you can test smarter, faster, and with more confidence. These tools help you catch problems early, validate recovery behavior, and ensure your devices and environment are ready for real-world deployment.
All right, thanks, Craig. That was really good. From my own experience, I can't stress how important this type of testing is in enterprise environments where data corruption, data unavailability is just not you can't do it, right? So testing like this is really important. Whether you're testing individual components like the initiators, targets, expanders, or an entire system, right? It's really important that we meet these enterprise expectations. And so all these, the exception handling and the error handling all has to be done very gracefully, and it's got to be tested for. So this type of testing is really essential. We have another poll question coming up. So again, we're looking for participation. So please, just all you got to do is go to the bottom and hit that vote button, and everything will be recorded. And with that, we're gonna hear from Paul. He's gonna focus a little more on the testing of cables and specifically around reliability. So Paul.
Hello, thank you for the introduction. My name is Paul Coddington, and today I will be talking about cable reliability. So, reliability is a key performance criteria for many applications, including AI, high performance computing, enterprise data storage. SAS technology, including SAS internal cables and SAS external cables, have been long known for their high reliability. So we're going to talk about reliability testing. We will start off with basic electrical tests. We'll go through a couple of those, then we'll go through a few mechanical integrity tests. Finally, we will go through several signal integrity tests. All of these will help with making sure that you have reliable cables. So we'll start off with the basic electrical tests. The HiPOT or DWV testing and the IR testing are very common tests for validating compliance with safety standards. In addition to those, you can check for opens, short circuits, and miswiring. Open short miswiring tests are simple DC current tests that can determine if a cable was built properly, the cable wires were connected to the right places, and checks for certain manufacturing defects or possible damage to the cables. I will point out that intermittent problems can be much, much harder to find because they might only present themselves in certain situations, such as when the cable is pulled, moved around, or the connector is wiggled in the port that it's plugged into. Those types of intermittent problems can be very difficult to find. Now we'll move on to some mechanical integrity tests. First, you'll want to check with the dimensional measurements. This involves verifying dimensional measurements in comparison to documented specifications that define the connectors that make up your cables. Some example SFF specifications are listed here for various common types of SAS internal or SAS external cables. If you need to locate one of these SFF specifications listed here or any other SFF specifications, you can find them on the SNIA SFF specifications page. The link is shown at the bottom of the slide. Continuing with the mechanical integrity tests, we'll talk about cable pull tests. These tests will check to make sure that the bulk cable wires will not pull out of the cable plug housings, causing breakage of the wire terminations or the important connections of the cable shielding. You can also do latching tests. This will ensure that the latches are functioning properly and that they can maintain the required minimum retention forces. This will help to ensure that your cables don't unintentionally or accidentally get unplugged when the bulk wire of the cable happens to get pulled or some other force gets applied to the cable or connector by some means. Basically, the latching makes sure that your cable stays connected and maintains a good connection. Moving on with some further mechanical integrity tests. You have these variety of cable flex tests that can be done. These tests, if required, are usually application specific and maybe customer specific too. A lot of times the flex tests are optional and are not needed for a cable that is intended to be plugged in once and hardly ever moved again, which can happen in a lot of instances in data centers. The SFF 8417 cable flex test, shown in the figure to the right, is sometimes referred to as the tick-tock test due to the pendulum-like back and forth motion that it does, much like a metronome. In addition to the flex test, you may want to consider doing some tether tests. Tether tests can check the toughness of the pull tab or lanyard, which may be part of the cable plug. Plastic pull tabs or lanyard parts can fail if the material is too brittle due to some poorly controlled molding process during manufacturing. Premature aging of some plastic materials can also sometimes result if the plastic compound pellets were not properly dried prior to the molding process, especially with certain plastic materials such as nylon, that tends to absorb moisture from the ambient air around them over time. Next, we'll talk about signal integrity testing for reliability. There's actually a whole series of SI tests for cables. I'll start off with the impedance test, a time domain measurement. The impedance test measures variations of the impedance along the signal path with a cable within a cable. A TDR is what's used to make the measurements. This is a sample TDR plot shown to the right with the various components of the cable assembly indicated on it, shown by the next to the effects that they've caused. Many of the SI tests can be done all at once and saved in S parameter files generated using a vector network analyzer, or VNA, and show how a cable's characteristics change with frequency. The standard format for these files is a touchstone SNP file, where N is the number of ports, such as S2P or S4P and so on. One of these S parameter measurements is insertion loss, which measures the amount of signal power lost as it travels through a system expressed in decibels. There's a simple sample graph to the right that shows what an insertion loss plot might look like. Insertion loss is important because it basically limits the effective reach or length of a cable. The longer the cable, the more insertion loss there is. This is why longer cables tend to use larger wire gauge sizes. Larger wire gauges have less insertion loss, allowing the cables to work at longer distances. Then you have return loss. Return loss measures the amount of signal that is reflected back from any discontinuity in the transmission line. It's also expressed in decibels. I provided a sample graph to the right that shows what a return loss plot might look like. Discontinuities and impedance mismatches can cause some harmful reflections, especially at higher data rates. All right, next I'm going to talk about some additional S parameter measurements. These S parameters measure the amount of noise introduced into a signal by the various types of crosstalk. The first one we're going to look at is near-end crosstalk, or next, which is a type of electromagnetic interference that occurs when signal from one wire pair induces noise onto an adjacent pair at the same end of the cable. You can see a sample of what a near-end crosstalk plot might look like to the right. In addition, you can also look at far-end crosstalk, or fixed, which is similar, but in this case, the electromagnetic interference occurs when the signal from one wire pair induces a noise on a victim pair measured at the far end of the victim wire, which is the opposite of the end opposite of the aggressor's signal source. The graph to the right shows what a far end crosstalk plot might look like. In cases where there is a lot of crosstalk, either next or fixed, the desired signals can get degraded and reduce the signal to noise ratio. it becomes increasingly difficult for the receiver to distinguish the signal from the noise, and this can cause data errors, increasing the bit error rate or bit error ratio to a point beyond what is correctable, leading to data loss. Another signal integrity test that can be done is skew measurement. This is another time domain test that involves very precise measurements. Skew is a timing difference that in the arrival times of signals traveling through various different paths within a cable assembly, often due to different path lengths caused by asymmetric geometry. As data rates increase, so does the importance of limiting skew. Too much skew can cause data to arrive at the receiver at different times, leading to data corruption and signal degradation. Finally, we have mixed mode SCD21, which is another one of the S parameter measurements. SCD21 is the unwanted conversion of a differential signal into a common mode signal. It indicates mode conversion, which can lead to signal degradation, distortions. Basically, a lower SCD21 indicates less mode conversion, which is desirable for reducing EMI emissions and noise, which degrades the desired signal. There are also other mixed mode S parameters like SDC21, which measures the common mode input to differential output. It's kind of like the reverse, right? This indicates a level of susceptibility. A high SDC21 indicates a significant conversion of common mode noise to the desired differential signal. A low SDC21 signifies very good isolation. This wraps up a number of the common SI tests that are typically done on cables to ensure high reliability for the user in their application. So, in conclusion, if you want highly reliable cables, which we all do, right? It is a very good idea to run them through a series of basic electrical tests, some mechanical integrity tests, and some signal integrity tests. There's a high likelihood that the cables will perform as desired if they pass these series of tests. Avoid letting your cables be the weakest link and that cause you headaches due to poor reliability. And with that, I am finished with my presentation, and thank you for your time.
All right, thanks, Paul. You know, I find that really interesting, especially with the role cables are playing in modern AI architectures, whether it's, you know, scale up or just the sheer scale of these systems. You know, I believe that this is going to be a hot topic for, you know, some time to come. It's interesting that a lot of the testing that, you know, Paul and Craig talked about, they can not only be used for, you know, full system integrity type tests, but also to test individual components. Like I touched on earlier, you know, with, you know, individual drives or initiators, to make sure that, again, they meet these enterprise expectations that I talked about earlier as well, right? So no data corruption, no data unavailability, right? Those are, you know, that's above and beyond anything, you know, any other client or other expectations. And so to meet that, this type of testing, is really important. So thanks, guys. One thing I should mention is that we keep talking about, SaaS, right? And that is the topic. But one thing I need to highlight is that, the majority of enterprise and data center SATA deployments use a SaaS infrastructure, right? So a lot of this testing, all of this testing is very relevant to, SATA running on a SaaS infrastructure. So very important in modern AI architectures, for instance. So now let's see if we can take a look at the poll results. So the first poll was, what are your biggest challenges ensuring quality and robustness? So we had a mix of performance and SATA protocol, right? And so I just touched on the SATA protocol, and it's interesting, right? SATA protocol brings an interesting dynamic because there are some, fundamental differences, and SATA was never designed to be an enterprise, interface, and now it's being used as such. And so it's interesting that, that is, still one of the bigger challenges. I guess any comments from you guys?
I would agree with you. Checking to see if
Yeah, we lost Craig's video.
yeah.
Yeah, I lost my network connection. I'm not quite sure why. I'm rejoining now. Hopefully,
Okay.
it works.
That's okay. So go ahead, Paul. Oh, there you are.
He's back.
So I don't know if you caught it, Craig. We were talking about the first poll question: what's the biggest challenges ensuring quality and robustness? And it was a mix of performance and SATA protocol.
Yeah, I'm curious on the SATA protocol. If anybody wants to type in the questions, what the challenges are there, that would be good to know.
Yeah, I would have thought I would probably leaned more towards performance.
Me too. Yeah.
But
So that's interesting because I can tell you that from my experience, right, in a lot of these really big, at scale systems, SATA can be problematic, right? Being fizz based, limited queue depth, right? In very congested topologies, SATA can be a problem. But interestingly enough, a lot of times it drifts into that performance, the SATA protocol.
Right. Which one is it?
Performance. So which one is it? So no, good conversation for sure.
Is it the performance that's causing the protocol issue?
Yeah.
Yeah. So yeah, and we could talk about that one for a while, I'm sure. Let me go to the next one. And this one was, when you have field issues, what percentage of the problems that you find make it back into your regression testing? I like this question because it's it gets you thinking, because there are a lot of different dynamics, and the results we got back are tipped a little more toward 10%. So the options were 0%, 10%, 25% other. And about 10% seem to be the sweet spot. And I would have to say, from my perspective, it's probably a little less than that, but in that neighborhood. And it's interesting because sometimes you find a problem or an issue that is, a complete corner case and it will never happen again, or specific to one revision of firmware, or something like that. But then there are some. A good example would be cable glitches, right? And that would fall into some of Paul's testing. We have found we've had problems where the problem then isn't recreatable. You have to go to a customer system and that exact port, and then you find out that the cable isn't secured properly, and it's glitching every once in a while. And so we make sure that we test so that if we run into that the drive will go offline, but then come back online, and there's no possibility of data corruption, right? So those types of things then make it back into our regressions. I guess thoughts from you guys?
Yeah, I think.
Yeah, that makes.
Go ahead.
I was going to say that makes a lot of sense. I'd wondered, you get the weird hardware problem, you fix it, it's fixed. There's no way to put that in the regression test. With the firmware problem, there's a possibility, if the bug, that somebody can reintroduce the bug. And that's where we try to make sure that we have a regression test around it. And performance problems. We do a lot of regression testing around performance.
Yeah, and I'll add that from a cable manufacturer's point of view, when issues come up with that affect one of the cables, then it's quite often that some sort of corrective action will be taken to prevent future occurrences of that same incident that caused the problem.
Yeah, so rather than regression testing, you may have manufacturing changes or something along those lines to ensure that doesn't happen.
Yeah, or maybe some additional testing to screen out certain components that may have contributed to the problem.
Okay.
Interesting.
Good. All right. Thanks, guys. So, those were the 2 polling questions. I want to turn to the audience questions. We have a couple, and I should note that anything that we don't get to, any questions that we don't get to, we will respond via email, and we'll answer all the questions. So the first one is, and I believe this is to you, Craig. Does this type of equipment do any sort of automated error checking?
Yeah, so we have traffic summary statistics where we automatically analyze the trace and look for any errors that are present in it and make those known. There's also what we have is some automated scripting where we have some example scripts that will run through and look for various things that are more specific that you may not be looking for every time, but it pertains to a particular type of communication, and so we'll have some automated checks to check for those, because it may not be a physical layer error, but it may be a protocol that's not behaving optimally.
So, and that's interesting. That kind of dovetails into the next question, and it's about can it be automated, right? Can
right.
A lot of these tests be automated? Because I could see, if you're trying to reproduce an issue or debug a specific problem, you might want, the full, the GUI and, just hammering on one thing. But if you're, trying to test a lot of things or need many, many passes at it, can you script to automate some of these tests?
Yeah, and that's a very good point, and we do that. I mean, it ties into integrating things into regression tests. The only way to do that is with automation. We automate everything. You really, in theory, don't even need our GUI. You can do everything from the API. So that's something that we do. It's part of our regression testing. We wouldn't be able to deliver our product to market without automation. And we do automation not just of our own product, but of other third-party tools that will stress the system. We automate those as much as possible as well.
Yeah, I mean, because automation is important for the big regressions. So from my experience, right, we have regressions running all the time, and we have to have a lot of that equipment, to do. And I'll kind of turn it back to Paul's stuff. Cable breaking, cable glitching, power cycles, things like that, right, to make sure that no matter what happens, you can recover from it, right? I mean, because bad things do happen, but you need to recover gracefully from those. So okay, very interesting. All right, well, thanks you guys. That was really good. As we wrap up, I wanna highlight the fact that the slides are available for download. There should be an attachments icon at the bottom of your screen, and you can select that. And then, on behalf of the SCSI Trade Association, I would like to thank you for attending our webinar. And I encourage you to go to our website. The website is awesome. It has current events, different news items, different upcoming events. We have a very robust product page, and just a lot of cool stuff, and a lot of hard work goes into that. We also encourage you to follow us on social media, and you can see the links on this last slide. So with that, thank you for your time. Good day.